Okay, I have the top of the hour, so let's get started. First of all, welcome. Thanks for joining me today. I am Greg Johnston with Sensors and Software. A little bit about me. My schooling was in geophysics. I'm currently a product manager, but I've been with Sensors and Software for 31 years. And I've had a varied path through research and development, programming, technical support, technical sales, marketing, and training. Okay, if you go to the Sensors and Software website and click on the Applications menu option, you will see this list. Notice that utility locating is high on the list. Without a doubt, the top application for GPR systems worldwide. I'm sure that many of you use GPR for utility locating. Trade magazines, YouTube, and LinkedIn are full of stories about this application. Well, today's webinar is not about utility locating with GPR. It is about all the other applications in the list. The ones that are less popular or even niche type applications, but still ones where GPR is used successfully. Here's a list of the GPR applications that I'd like to talk about today. As you can see, it's a long list and I only have a short amount of time. So I'm going to cover a lot of ground today. So buckle your seatbelts. Okay, I am not going over GPR theory today. I assume that you know enough about GPR to be here today. But what I do want to mention is that GPR can be collected in several ways and displayed in several ways. So I want you to have a better understanding of what you are looking at as we go through lots of data examples. The first type of data collection is called a line scan. It produces a cross-sectional image, a vertical slice under the GPR survey path. This is an example of it here. You will see lots of GPR cross-sections in this presentation. Here are examples of collecting line scans. As you can see, there are many ways to move a GPR system across the surface. Most of these methods rely on an odometer wheel to collect data traces at equal distance intervals, but not all. Note the data collected on the water. There we are using free run mode to collect the data. A bunch of parallel line scans produce a grid scan. This image shows the idea of a GPR grid survey, collecting data over an area like you are mowing the lawn. Once we collect GPR data over an area, now we can present it in more powerful ways, depth slices and even 3D. Depth slices are maps of the GPR reflection strength or reflectivity at a certain depth. Some reflections are weak, shown here in blue, and other reflections are stronger, shown here in red. Here's an example of a buried water jug collected at a forensics training course for one of our customers. In the cross section on the right, you see the strong response in the GPR line at a depth of about 3 feet. On the left is the depth slice at 3 feet, the water jug appearing as a red spot. The depth slice makes the position of the water jug obvious and even provides some coarse information on the approximate size and shape of the target. So hopefully that orients you to what you're going to see today. A lot of GPR data displayed as cross sections and depth slices. Okay, let's start with arguably the second most popular application of GPR, concrete scanning. Concrete is a good medium for GPR penetration for about 30 to 80 centimeters or maybe 12 to 18 inches. Sometimes you can see deeper in concrete, but it can often be challenging. GPR can image objects within the concrete. This means rebar, conduits, post-tension cables, and other objects. This example shows the concept of collecting the data on the floor and you can see the rebar in the depth slice that's displayed on the floor photo. The main reason that concrete scanning with GPR is popular is for avoidance. GPR images allow cutting, drilling, and coring the concrete with much less risk of hitting an embedded object. Cutting through a post-tension cable or a conduit is not good for obvious reasons. Even cutting through rebar is frowned upon by structural engineers. So here's a good example of GPR data, a GPR data depth slice showing a conduit to avoid. You can see the pattern of the rebar in the square pattern, but then you have an object that's going through the area at an angle, more than likely a conduit and more than likely something you want to avoid. The other reason to scan concrete with GPR is to understand how a concrete structure was constructed. Especially if there's no as-built drawings, which is very typical, especially for older structures. Is there rebar? If so, what is the rebar spacing? What is the depth? How uniform is it? Are there gaps in the rebar placement? Could the cracks we're seeing in the concrete have something to do with the embedded objects? This is all information that structural engineers want to know before renovating or adding to a concrete structure. This is a great example that shows how the placement of reinforcing metal varies across a structure. Scanning concrete can also be used to confirm for quality assurance that the contractor built the structure as specified. Here's an example that shows the suspended slab thickness. You can see the reflection. The long continuous reflection at the bottom is showing the slab thickness. It also shows the rebar tied to a vertical column. And this is definitely something you want to ensure was done during the construction. GPR can also image other objects in the concrete. For example, radiant heating tubes, as this example shows. In this example, two grid scans are combined together to generate depth slices. The shallow depth slice shows the reinforcing metal. A deeper depth slice shows something else running through at an angle, perhaps a conduit. So here's a 10 meter by 5 meter GPR grid collected on a concrete bridge approach slab, the area of the road just before the bridge deck. As you can see, the detail is tremendous. If you understand how bridges are constructed, you're going to know what each of these elements are. Here we've got somebody who's interpreted tie bars and dowel bars, as well as the transverse joints and rebar and that sort of thing. I'm not a bridge deck engineer, but this was interpreted by somebody who knows how these structures are constructed. Let's now talk about my personal favorite use of GPR, which is archaeology. Love Discovery Channel, love watching those shows about ancient civilizations. Here are Roman era graves in North Africa plotted as a depth slice. Notice that this grid is 7 meters by 13 meters, which is much larger in area compared to most of the concrete grids we were just looking at. When looking at GPR data, the first thing you look for is the scale, because GPR data can vary from a small 2 foot by 2 foot concrete scan to literally hectares of data, as you will see in a bit. The objects that cause the strong reflections are interpreted as being caused by sarcophaguses or sarcophagi, I guess, something like this. And we think it looks something like the photo that's shown here. The strong response from the air-filled sarcophagi are the largest contrast of anything in the area. So the graves stick out dramatically and are easy to interpret. Just remember that any interpretation is based on context and other information. I would not interpret this as Roman graves if it was collected in Denver, Colorado. Here's GPR data, grid data, displayed as depth slices, where the reflection strength is shown in 3D. It's an interesting way to highlight the area of interest. The circular feature that emerges from the data as you slice downward is interpreted as a Viking grave. This is a very old data set from the early 2000s, but is still classic archaeological GPR data. It is notable because it was, to my knowledge, one of the early large-scale GPR grid scan surveys. The basic story is that this area in Austria is a well-known Roman archaeology site, with many Roman ruins visible on the surface. Researchers at Archaeoprospections wondered what might be hidden under the open fields in this photo. So they went out with a 500 megahertz GPR system. They collected an area 160 by 250 meters at a line spacing of 0.5 meter, which is tremendous data density. If you do the math, that is 80 kilometers. That's 80 line kilometers of data. And they collected that data to a depth of about 2.5 meters. The researcher that collected this data spent 11 days collecting the data, averaging about 7 kilometers of data per day. Here's the depth slice animation from the surface to a depth of 3.4 meters. So each slice is 10 centimeters deeper. So there's 34 frames in this animation. You can watch this animation over and over again and see new features every time. Walls, interior walls, curved walls, doorways, changing floor materials, and my favorite feature. If you watch this area of the animation, you will see the strong GPR reflectors sweeping towards the bottom of the slide as you slice deeper in the ground. What would cause that? Something that moves laterally as you slice deeper into the ground. Stairs. Very cool. Since that survey, various groups around the world started collecting data with multi-channel GPR systems to cover a wider swath and speed up data acquisition. This is a SPIDAR system that consists of 7 transmitter-receiver pairs of 500 megahertz antennas. Multi-channel systems simply make acquiring data over larger areas faster and more efficient. Now, practically weekly, you're seeing amazing archaeological work from around the world collected with GPR. For example, in the summer of 2021, some of you may have heard about the GPR survey done in Filari Novi in Italy, north of Rome. I apologize to all Italians for butchering that name. An entire Roman city was surveyed using a sensors and software SPIDAR system. The data really speaks for itself. Buildings, streets, even at this scale, you can see the amphitheater. And when you zoom in, I'm sure there's much, much more to keep archaeologists busy for years to come. Let's move on. Let's talk about voids, cavities, fractures, and tunnels. GPR is really good at finding voids, cavities, fractures, and tunnels. The main reason, as this example shows, is an air-filled void like this car tunnel provides a large contrast with surrounding material and produces strong reflections. Rock has a dielectric permittivity of 6. Air has a dielectric permittivity of 1. The reflectivity of a tunnel or cave or cavity is 42%. This high reflectivity means the car tunnels show up as strong reflections in the GPR data. Now, keep in mind, the same is true if the void is water-filled. You still get that high contrast reflectivity. Voids can be at all different physical scales, from fractures in rocks that are millimeters in aperture to cavities tens of meters across. The good news is that from a GPR point of view, the physics is exactly the same, and therefore there's a high chance of detectability in many cases. The ability to detect voids is useful information because we know from our everyday experiences that voids can cause problems in our society, as these images show. Here's an example of GPR data showing caves in limestone. The strong reflectors indicating a strong contrast in materials. Here's an example of GPR detecting a clandestine tunnel. You can even tell that the top of the tunnel is flat. Here's an example that a customer sent me. The short story is that a plane being moved at an airport suddenly collapsed into a hole that opened up in the concrete, causing $1.5 million in damage. Luckily, no passengers were on board at the time. Now, of course, airport officials were concerned that if there is one cavity, there might be more. So they hired our customer to survey the airport taxiways with GPR. This is an example of one of the grids that was collected. And if you slice down through, you see this large red area. In this case, red is being depicted as a strong reflector. And this is what the cross section looked like. So there is actually a hyperbolic response that you can see in this, and that's actually from a pipe that was running nearby. There was a suspicion that somehow the voids were associated with liquids leaking from pipes, and so the surveys were done close to pipes, and this is what they found. Was at this one pipe, you could clearly see that there was something going on adjacent to the pipe. And we got this very strong response that you can see both in the cross section, but also in the depth slice. And when they probed it, they found that it was a cavity, and then they had to make it safe. So they had to repair it before it collapsed and became a hazard. And so that's where the cavity was indicated both in the cross section and in the depth slice. Okay, now this is an entirely different scale. So watch this one a couple of times here. So this is a depth slice animation from a GPR survey collected at the bottom of an open pit gold mine in Canada. The depth slices are going from 19 to 26 meters. So that's 1 meter per frame. So light blue and yellow indicate weak or no reflections, something that you would expect in a relatively homogeneous rock with no fractures or cavities in it. If you watch the animation at about 25 meters or about 80 feet deep, there are suddenly strong localized reflections colored in red. What is likely to have strong contrasts 25 meters deep? It's interpreted as old underground mine workings. This mine was originally an underground mine, and then with modern technology, they basically turned it into an open pit mine. And so as they're working away in the open pit, every now and then they come across these old mine workings, and you can understand the problems that could cause. So obviously this is something that may cause problems when they mine down to it. But with GPR, we are recognizing that it's there 25 meters before they're encountering it. So with this knowledge that something is there, they can rescan as they get closer and mitigate any potential problems that this reflector is going to cause. Okay, so going from 25 meters to 10 centimeters, or from about 80 feet to 4 inches. To the GPR, the physics of a void under concrete is exactly the same. So it doesn't matter the scale of the void, it's the same physics. High contrast between the concrete above and the air in the void below. So here the GPR is identifying an area where there's a gap underneath the concrete slab. There's an air gap. And so we're seeing a strong reflector. And it's something like this. This isn't the exact picture from this particular site, but it's that idea, a void underneath the concrete. And you saw in the picture earlier, you know, the famous one is the forklift that falls through the concrete slab in a warehouse somewhere. So now everybody's worried, you know, how extensive are the voids under the concrete slab? Well, you can find that with ground penetrating radar. So here's an example where they collected a grid of data 10 feet by 22 feet. When they depth slice down to just under the concrete, there are anomalous high amplitude reflectors that were interpreted as possible voids and ended up being confirmed by drilling. The nice thing with GPR is that it provides a good indication of the aerial extent of the void. If you scan a homogeneous or uniform material, there's no contrast, and therefore you don't get any GPR reflections back. Now, this is very rare, as most materials, even snow and sand on a beach, has some sort of structure to it that GPR often reveals. If we think about rocks like granite or marble, they do tend to have a very consistent structure, except for one thing: fractures. They tend to crack. And GPR is an excellent tool for seeing fractures in these types of rock. Here's an excellent example from a marble quarry in Greece. Notice that the cross section on the right is quite long. It's 260 meters long. So we got a lot of data compressed into this one image. But what it shows, it's showing areas where the rock is highly fractured and other areas where the rock is more uniform with fewer reflectors. This is very useful information to help rock quarries plan their future production. At a smaller scale, you can scan stone blocks with high frequency GPR and detect interior fractures and voids to assess the overall quality and to better predict the economic yield from that block when it's cut up. So here you can see these reflectors on the inside. The reflector at the very bottom here is from the far side or the bottom of the stone slab or the stone block. And the reflectors that are inside are probably things like internal fractures, things that they're going to be concerned about when they cut this block up. So we can show this in a 3D plot. So here's a slab slicing through, and you can see the strong reflectors on the inside of the slab. And then we can change the opacity to only show the strongest reflectors inside the slab and then spin it around so that we can see the geometry of these internal fractures, or, you know, at this point we can really just say heterogeneities. We don't really know what it is for sure, but it's likely, the likely interpretation is some sort of cavity or fractures inside. So another place where there is concern about fractures is in underground mines, because fractures can lead to dangerous ceiling collapses or rock falls. Here's an example that I have data set from underground potash mining in Canada. Here is how one customer there is using GPR to image upwards to look for fractures or separations in the rock. So you can see the different ways that they are deploying the GPR, looking upward. And if you look at the image, this is a GPR image basically plotted upside down. It's looking up. So as you go upward, you're going up into the rock above the ceiling of the mine. So what we see in the data is we see these semi-continuous reflectors, which turn out to be clay seams. And if the clay seams are too close to the cutting face, miners are concerned because that's an area that can separate and collapse. The GPR makes it possible to detect these clay seams and deal with them before they become a danger to the mine workers. Okay, let's talk about roads and runways. As most of you know, GPR does not penetrate deep everywhere. There are soil types, for example, clay soils, that limit GPR penetration. So you may go out to a job site with the GPR and find out that it is not penetrating deep enough to solve the problem at hand. This is every GPR operator's frustration with the technology. However, using GPR on human infrastructure has a higher than average success rate. So GPR works well on concrete, as I've already mentioned. And my experience is that it often works well on man-made structures such as roads, bridges, and runways. Let's look at some examples of these applications. So there's no easier way to collect GPR data than to sit in your vehicle and drive as you tow it behind you. It's easy to collect large data volumes very quickly. But what information can GPR provide on roads? It can measure layer thicknesses, such as the asphalt thickness and base course thickness, to make sure that they are up to the engineering standards. This can help to quantitatively measure road condition and allow for informed decision making about future maintenance. So here's a 100-meter long GPR survey conducted on a test road at the University of Waterloo. We can see two boundaries, the bottom of asphalt and the bottom of granular. You can also see a 10-meter section of road where the asphalt is thicker than everywhere else. I think it was just done because this is a test road. Now, GPR data was collected on this road with a very complex history. So here's how I would interpret this. The top of the image is the top of the asphalt. I can see that on the surface. I see hyperbolic responses that sure look like rebar. So there's likely a concrete slab at depth. The reflector above the rebar responses is probably the asphalt concrete interface, or the top of concrete. The reflector below the rebar responses is probably the bottom of concrete. Everything between those surfaces is the concrete slab. Now, everything above the concrete is asphalt. But what I see a break in the rebar and in the asphalt that is probably a repaired zone. So originally, this road was constructed as a reinforced concrete road and later covered with asphalt. A lot of information that we've gotten out of the GPR data. So roads are supposed to be consistent and uniform. Consistent asphalt thickness, consistent base course thickness. They often core roads to confirm this, but they often core randomly or at equal intervals. What GPR is really good at especially in enormous data sets like what you get when scanning roads, is it shows anomalous areas. That is, locations that are different than everywhere else. The places that break up the consistency I talked about. This is a good example of a subsurface anomaly revealed by GPR. What the heck's going on here? I have no idea. But if I wanted to know, I would know exactly where to core to find out. So rather than coring randomly or at equal intervals, which is expensive and inefficient, target the coring to the potential problem spots revealed by the GPR. Runways are another piece of infrastructure that we all want to be well maintained. GPR is an excellent tool for inspections, specifically finding anomalous areas that may be problems in the making. Here's a depth slice animation of a runway at a regional airport. And I don't want you to think that everything that is red on here is a big cavity or something. Obviously, it needs a little bit more work. You can get soil layers that will give you strong reflectors, but we can note a few things in the data. And by collecting data annually or every few years, you're able to time lapse it to see what is changing in the data. Because changing areas are probably not good. We want to know what is changing. Is soil being washed away? Is a cavity forming? That sort of thing. So GPR gives you the ability with annual surveys to create time-lapse images of structures. Okay, let's talk about GPR and bridges. Bridges are critical infrastructure, and they cost a lot to rehab or replace, not just in terms of the work itself, but also to the local economy in terms of delays and inconvenience to the public during construction. One piece of information that bridge engineers want is, when does the bridge deck need rehabilitation? The answer to this question affects the Department of Transportation planning and budgets. There are various ways to inspect a bridge deck, both destructive and non-destructive. A few years ago, the US Transportation Research Board ranked GPR as the most effective technology for detecting delamination, corrosion, vertical cracks, and concrete degradation. So there's an ASTM standard that describes the process of using GPR to evaluate the condition of bridge decks overlain with asphalt. For those who are interested, this is ASTM 6087. Here's the premise of the ASTM standard. If you have this scenario of a reinforced concrete bridge deck overlain by asphalt, if the bridge is uniform, if you run a GPR survey on the bridge deck, the reflections from the rebar will be similar, because all the material above is similar. So there's no reason why the signal wouldn't be very similar. So you might expect to see a GPR cross-section like this, where the hyperbolas from the rebar look very similar. And not just qualitatively. We can extract the reflection strength of each rebar reflection and create a quantitative map of the reflection strength. If the reflection strength of the rebar is within a few percent, it is a reasonable conclusion that the bridge deck is in good shape. Conversely, if the rebar reflection strength varies significantly across the bridge, we can conclude that something has affected the bridge deck. Let's look at some of the typical culprits that affect the reflection strength of rebar on bridge decks. Say there's delamination between the asphalt layers and the concrete deck. Or there's chloride infiltration into the bridge deck, often caused by dumping salt on roads to prevent ice and snow buildup in the winter to make driving safer. Or the rebar is corroded. The asphalt is cracked. or the concrete is cracked, or more likely, some sort of combination of all these issues. So in these situations, the rebar reflection strength will not be uniform. If we look at the reflections from the rebar, we're going to have a variation where there's a problem with the rebar or above the rebar. The rebar reflections from the problem areas will be weaker compared to other areas. The result will be a GPR cross-section that looks something like this. The problem areas show up as weaker rebar responses. Again, we want to be quantitative and not just qualitative, so we extract the reflection strength of all the rebar and generate a map of the reflection strength to see the variations across the bridge deck. So here's an example of such a map. Now, I have inverted the color table, so the areas of weaker rebar reflections are shown in red, and the areas of strong reflectors are shown in blue. The idea being red is bad, blue is good. But this it would be a typical, or at least an example of this type of map. Now, traditionally, if you want to know the condition of a bridge deck, you core, which of course is a destructive method. And because you don't know where to core, you core randomly or systematically to try to provide a quote unquote representative data set. So here's the GPR signal strength map on a bridge deck. And as you can see, the information provided by the GPR allows you to target the position of cores to the problem areas, saving time, money, and the amount of destructive coring done to the bridge. Moving on, let's talk about forensics. GPR is a natural tool for forensics because law enforcement often needs to look for buried evidence. And GPR has the great advantage of being able to image non-metallic objects. You saw this slide earlier showing the relationship between GPR cross-sections and depth slices. Here it is used as a forensics case study as an example of a buried water jug collected at a forensics training course for one of our customers. It shows the power of GPR for finding buried non-metallic objects. I want to show several real-life examples where this is an advantage for law enforcement. So number one here, looking for buried containers of explosives or dangerous chemicals. This happened in a case in Canada a few years ago. A guy had buried some pretty scary stuff in his backyard and was stockpiling it for who knows what. Finding buried weapons. And again, metal objects can be found with other technologies, but GPR is going to be the advantage for finding plastic or wooden objects. Finding caches of drugs or money. A US police department contacted us a few years ago and said that they had found $500,000 in drug money buried in a drug dealer's backyard in plastic Tupperware containers. GPR is one of the only technologies that could detect something like that. Now, you do have to set realistic expectations. So the GPR is unlikely to find very small objects or containers like the ones shown here. Another example is of the type of things that you want to find are clandestine graves. And certainly that's one that's been in the news an awful lot over the last couple of years, especially in Canada, with the residential school grave searches and that sort of thing. So we're basically finding graves that are unmarked. Now, I did an entire, I think it's about an hour and 50-minute long webinar about this topic in August 2021. And for those of you who want to take a deep dive into this topic, it's available on our website or on the Sensors and Software YouTube channel. So today I'm just going to show a few examples. Providing the GPR signals can penetrate the soil, which is not always a given, finding graves with coffins is pretty straightforward, as this example on the right shows. Clearly, we can see coffins at different depths, different spacings, and different materials as well. So here's the situation. The contrast between an air-filled coffin in a dry soil is large, resulting in about a 38% reflectivity. This is why coffins show up quite well in GPR data. Here's a GPR depth slice superimposed on Google Earth. The red responses show are interpreted as the graves of African American slaves in the United States. You can see that they were found in a cemetery, but in this part of the cemetery, there are no markers for these graves. No one knew how many graves were there until one of our customers did a GPR survey at the site. Here's a depth slice animation of a 20 meter by 20 meter area showing coffins at different depths. You can see them appear and disappear, some of the shallower ones versus deeper ones. A very powerful way, the depth slicing, a very powerful way of looking at the data this way. We can also look at data in 3D. So here's a grid of GPR data collected as cemetery showing coffins or the burials in a 3D display. When we're talking about trying to detect bodies without coffins, which is a situation police may run into, after a few years, it becomes a very challenging task because of all the contrast and materials that GPR relies on. All that contrast is gone. At that point, we have to start looking for indirect evidence that a body is buried. For example, the soil disturbance created by burying a body. Again, this is a great example of GPR showing an anomalous area, an area that is different than everywhere else around it. Okay, so here's an example of an 80 meter long or a 260 foot long line. And it doesn't take a lot of training to see that there are 4 places where the soil has been altered, or perhaps a hole has been dug. So if you're looking for something buried, such as a body, here are 4 prime locations to start your search. Let's have a brief look at environmental applications. One environmental application of GPR is detecting USTs, or underground storage tanks. Here's a great example of a GPR cross-section across 2 tanks. If you look at it closely, you can even see the edges of the pit that was dug to bury the tanks. Plus, you can see other reflectors in and around the tanks. Another example that shows 5 underground storage tanks at a gas station. You can't extract the diameter of the tanks, but in the depth slice, you can tell the approximate length of the tanks because the reflection just drops off right at the edges here. So we got a pretty good idea of the length of the tanks. But as some of you know, determining the exact diameter we're not going to be able to determine that with the GPR data. So in this case, because the data was collected with GPS, we're able to display the depth slices on Google Earth. And just one look at this. It's such a powerful way to convey the results of the survey. Bathymetry, measuring water depth. So GPR data collected on fresh water, and I'm emphasizing fresh water, with low TDS, or total dissolved solids. So that's what we've got in the example here. So keep in mind that water with high TDS, for example, salt water has very extremely high total dissolved solids. That water attenuates the GPR signal quickly and reduces GPR signal penetration into the water. In the case of salt water, that attenuation occurs in millimeters. So we really can't use GPR in salt water, as some of you will know. So inappropriate freshwater penetration can be quite good, allowing you to measure the water depth and even see into the sub-bottom. Notice the little hyperbolas. If you look closely, you can see there's little hyperbolas in the soft sediment on the bottom of this lake. These are objects. Now, perhaps they're just rocks, but perhaps they're something of more interest. We've identified them. We know where they're located with the GPR. If you use GPS to position your survey, you can create maps of the water depth. In this case, they were worried about this municipal pond silting up. So they measure the water depth annually with GPR to know when it is time to dredge it. Let's talk about agriculture and forestry. GPR can be used for locating and mapping non-metallic drainage tiles. Data can be collected with a smart sled, as shown here on the left. There are some artifacts in the data from the system bouncing up and down over the furrows in the field, but the drainage tile hyperbolas are often visible. So we can see here. Here they're marked in, they've been interpreted with a green dot and a very weak blue dot and also a weak yellow dot. And if we look at the data all together, if you collect the data with GPS and you pick all those hyperbolas, put colored dots on them, the drainage tile pattern emerges from the data. In this case, you can see how the green and yellow dots line up into the likely path of the drainage tile. So here we plotted the interpretations on Google Earth to see the position of the drainage tiles in the context of where the data was collected. Tree roots. GPR is sensitive to tree roots, which if you think about it, are non-metallic water-filled pipes. And you can see the strong reflections in the cross-section on the lower left, and even plot them in 3D on the right. Here's another example. So they collected a grid of data in this area. Here's the depth slice superimposed on it, showing the tree roots. This image, which I turned on its side to plot it larger on the slide, shows the tremendous detail that GPR can provide in mapping tree roots. Just have a close look at that. It is amazing detail. Again, one of our customers collected this. I forgot to acknowledge him on this slide. I should have acknowledged the company who collected this. My apologies. Okay, now we're down to geology. And this application is at the roots, if you pardon the pun, of sensors and software. The first GPR systems we developed were low frequency GPR systems to try to see as deep into the ground as possible for geological structures. So here's a few examples. Here's an example in a sandy environment, which some of you will know is an ideal material for deep penetration with GPR. If you look at the scale, 20 plus meters of penetration, showing lots of structures, dipping beds, dipping in opposite directions. This is all information that can be interpreted by geologists. And this is how it was interpreted. So they've interpreted the two different sand units on the top, a till layer and a bedrock. Again, this is an interpretation. This is not confirmed. You cannot get this information from the GPR image itself. GPR does not provide compositional information. You've got to use other information, all the information you have to make the best interpretation possible. So here's a river delta, and let's look at some GPR data collected across a river delta. So here's the structure as revealed by GPR. Again, look at the scale, 500 meters long, and we're getting 30 meters of penetration in some spots. So tremendous area, great for GPR. So we see 4 set beds. And because these signals attenuate so quickly at a depth of 22 meters or so, the interpretation is that the whole area is underlain by clay, because the GPR signal attenuates and is gone very quickly. This is one of the deepest GPR cross sections you will ever see. 50 meters of penetration. What is that? About 170 feet or so. Very, very deep. The vast majority of places in the world, you will not see this deep. This was actually collected in the Upper Peninsula in Michigan, which is an area that's terrific for ground penetrating radar, for deep ground penetrating radar. And it was collected with 100 megahertz antennas, not even the lowest frequency antennas that we have available. So you can see all the structures, and here is how the professor who collected the data interpreted those structures. Aeolian deposits and barrier bar and all sorts of terms that I'm somewhat familiar with from long ago in university, but have forgotten recently for sure. But this is the information you're extracting from the GPR data. Here's another one, higher frequency, 250 megahertz. So we're only looking 7 meters deep. Now I'm saying only 7 meters, but 7 meters with 250 megahertz is tremendous. Wish we could see that everywhere. And I like this example because it shows a combination of two things. We've got the actual geology, and we have the GPR revealing man-made buried objects. Here's a great image of a buried river channel. This is the type of structure you want to find if there's a history of gold deposits in the area, because the heavy gold nuggets tend to settle at the bottom of rivers. So that's where you want to go and look for them. So tremendous example of that on the surface, you would not even know that this was an ancient river channel, but the GPR reveals the structure underneath. Here's some data collected on volcanic ash, and this is relatively recent volcanic ash. This is a volcano in Nicaragua that is, I guess it's currently active, and it's certainly been active over the last 200 years. And so here's a GPR cross section. This is a kilometer long, collected by this professor. Kilometer long, so keep in mind, looking about 20 meters deep. And you're able to follow all these reflectors for hundreds of meters. So tremendous imaging. Military and security. So we've already talked about GPR being used to detect clandestine tunnels. That's one area where it's used in military and security. But let's look at using it for other military examples. So the fact that we can find objects in the ground with ground penetrating radar means things like unexploded ordnance can be, this is one of the technologies used to find unexploded ordnance. Here's a photo one of our customers sent us of collecting GPR data, looking for landmines, looking for mines on roads in Africa. This is about 20 plus years ago. And you can see we've got a number of GPR systems collecting multi-channel data, surveying the road. And if you have a look at this vehicle, it's built to be as light as possible, low pressure tires, spread out. So if it drives over a mine, it's not going to set it off. So I hope that guy got paid danger pay for driving this thing. GPR also, it's an important technology to find anti-personnel mines, which are difficult to detect because they have so little metal in them. A lot of plastic, a lot of wood, that sort of thing. And we did some work with the Canadian military 15 plus years ago, showing how ground penetrating radar can detect these sorts of objects. So we buried them in controlled pits and then showed how they could be imaged with ground penetrating radar. So GPR is part of the solution for this particular problem, but I dare say my experience is that it's not the only solution. You really need to throw multiple technologies at this problem. Okay, the last one, and my time is almost up. Ice and snow. Ice is really a special medium for GPR because it's so transparent. GPR signals can travel great distances in ice, as you're going to see. And in northern areas of Canada, Alaska, and Europe, people travel on ice roads in the winter. These are roads made across lakes and rivers. So we have a GPR system called IceMap that is used to ensure ice roads are thick enough to support the trucks going over them. Over the last 20 years, monitoring ice roads has really become routine in these jurisdictions. So this gives you an example of how the ice map works, what it looks like, and what the data looks like as it's scrolling on the screen in real time. And IceMap allows the ice thickness maps. It allows ice thickness maps to be made over long distances and quickly identify the thin spots that need to be flooded or avoided so that they're safe. GPR has been used for studying glaciers for decades. Great example of what a glacier kind of looks like, and then what the GPR cross section looks like going over the glacier. So you're seeing 40 or 50 meters through the ice into the bottom and into the sub-bottom underneath the glacier. And especially now, because glaciers are melting around the world, GPR really provides a means for estimating. If you time lapse, if you collect the data multiple times, you can estimate the melt volume. Here's an example of really deep penetration with ground penetrating radar. And again, ice being the important part of this equation. So this researcher collected 25 megahertz and data over a couple areas in Antarctica. And this is a 5-kilometer long section. It has tremendous vertical exaggeration. It's 5 kilometers long, but 800 meters deep. And you can actually image the whole shape of the glacier coming down this valley to 800 meters. Unbelievable in my mind. So excited when I saw this for the first time. And if you zoom in on the first 250 meters, you can see the structure of the ice and other objects within the ice. So amazing imaging. So here's another one on the ice, on the floating ice. So in this example, you're looking through the ice shelf into the ocean underneath. So the ice is floating here. And the example here, we're seeing like 600, 800, 1,000 meters in the ice. And we're getting in the area where it's grounded ice, where the ice is still on the continent, you can see a reflection down here that's about 1,100 meters below. So tremendous penetration in ice. Okay, so that's 1 hour exactly looking at it. So I hope you enjoyed this webinar. I hope it gave you some ideas of what ground penetrating radar can be used for. You're welcome to join us at the next webinar, which is on November 1st, which we are presenting in conjunction with the Excavation Safety Magazine. And this one I am going to talk about utilities. So it's called Mapping Utilities with LMX GPR. So after this webinar, we'll email out a link to all the registrants so that you can register for this webinar. So I hope you can make it.